All right, example 9. A boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 0.6 meters higher than the bow of the boat. Wow, that's. So let's think about what's going on. So we have a boat. Let's draw a cool old boat here. Make mine a canoe. There we go. Fly. There's my boat. And if you can't draw a boat as well as I can, and you can kind of put some like detail in here, so it kind of looks like the inside of the boat. Now it looks like kind of a loaf of bread.
It looks like a
anyway,
flag.
There we go. Yeah, we need like a little.
Looks
there
like
now it looks like. There we go. All right, now it looks like a loaf of
egg.
bread with a little flag in it. Anyway, so we got our boat that's on the water, right? And here's the water. It so happens we have a blue boat on the water. And the bow of the boat, if you don't know anything about boats, the bow is the front of the boat. All right, and it's going to a dock. Let's make the dock brownish color here. That's kind of brownish there. Here's my dock.
Noise.
All right, there's the dock. And there's a rope attached to the bow, passed through a pulley on the dock that's 0.6 meters higher than the bow of the boat. So, our rope's going to be this purple color. There we go.
The duck.
That's not where it is. Let's try again. All right, there's like a little pulley right here. So there we go. So we see what's going on there? Can we figure this out? All right. Now, what we have to do is we have to mark some dimensions on this thing that we just drew. And if I were to establish a couple things, the boat is moving towards the dock horizontally, right? So even though this rope's attached at a vertical tilt a little bit, as the rope gets pulled in, the boat's going to stay on the water coming horizontally towards this dock. All right? Looking at this picture, is the green dimension changing?
Yes.
Yes. So I'm going to call that X. Is the magenta dimension changing?
Yes.
Yes, the rope's being pulled in, so it's getting shorter, right? So let's call this R for rope. Is the pulley or the bow of the boat changing any vertical position whatsoever?
No.
No. The pulley's right here, the bow of the boat's right there, the boat's moving horizontally. So this distance here is going to stay the same all the way through, which is, if we read again, 0.6 meters higher than the bow of the boat. So 0.6 meters. That's not changing, so we're going to use an actual number there. All right? And again, when you draw your picture, that's the type of thinking you need. What's changing, what isn't changing. If something's changing, represent it as a letter. If something isn't changing, represent it with a number specifically in the picture. All right? Looking at that picture, I'm looking at a right triangle. And as with all the other right triangles, whenever you get a right triangle, the Pythagorean theorem is going to come into play. So leg squared plus leg squared is equal to hypotenuse squared. So x squared plus 0.36, which is 0.6 squared, is equal to r squared. All right? So the Pythagorean theorem relates the variables of the change in x and the change in r that we're going to be dealing with in this problem. And the only rate they give me in the entire problem, if I keep reading, if the rope is pulled in at a rate of 3 meters per second, so what's that? Is that dx over dt or dr over dt?
dr over dt.
dr. And is r getting bigger or smaller based on that?
Smaller.
Smaller. It's being pulled in, so the rope is shrinking, right? So when we look at this, we're going to have x equals something, r equals something, dx over dt equals something, and dr over dt equals something. We know that dr over dt is going to be negative 3 meters per second. And it makes sense that we should get dx over dt being a negative value here also, right? Because if r is shrinking, then the boat should be getting closer to the dock. If the boat's going away from the dock while the rope is shrinking, that means your rope broke and you're in trouble. So if you're doing this problem, you get the wrong sign on your answer, just know that you probably messed up somewhere. So be careful and take a look at your work. All right, how fast is the boat approaching the dock when it is 5 meters from the dock? All right, now, when it's 5 meters from the dock, are they talking about x or are they talking about r?
X.
They're talking about x, right? So x is 5 meters. So r, to find r, which again, when we get a Pythagorean theorem, 2r dr over dt, r is going to show up in our derivative, right? So we need to know what r is. To find out what r is, I just apply the Pythagorean theorem. 25 plus 0.36, so r squared is equal to 25.36. So r is going to equal the square root of that. 5 5.04, I don't know, my calculator's like disappeared from me here. Oh, there it is, it's underneath all these papers that I can see it. All right. The square root of 25.36, 5.04, how about that for a guess? 5.0359. If we want to go 4 decimal places like we usually do. But that does round to 5.04, so it's a heck of a guess. All right. So the rope is that long, the ship is 5 meters from the dock, and dx over dt is what we're looking for. I have an equation relating the variables I'm working with. I know exactly how much the variables are worth. I know one of the rates, I'm looking for the other rate. Relating equations there. Everything's ready to go for differentiation and solving. So, derivative of x squared is 2x. I'm going to put a dx over dt because x is not t. The derivative of 0.36, or any number therefore, is 0, equals derivative of r squared is 2r dr over dt. As always with the Pythagorean theorem, we can expect the 2's to cancel, and they do just that every time. It's awesome when that happens. It gets numbers smaller and makes it worth doing. At this point, I just got to substitute what I know. All 3 of these numbers go in. This is what I'm looking for. So x, which is 5, dx over dt is what I don't know yet, equals r, which is 5.0359, times dr over dt, which is negative 3. So to get dx over dt, I just have to take this product and divide it by 5. And I can just type that in my calculator exactly as it's written. So 5.0359 times negative 3 divided by 5 comes out to negative 3.02. That's meters per second. Going back to the whole exact answer, not exact answer type thing. If I wanted an exact answer, if I kept this as the square root of 25.36, this would be the square root of 25.36. Then you can go ahead and get times that over that, get some decimal, some radical answer. That would be the exact answer. But again, for the sake of what we're doing, an approximate decimal answer, 2 decimal places is fine with me. That will do the trick.